about DSL. So the one way to increase the speed is to make this line digital, the access line digital. And basically that's what the phone company did. You take the bits, actually you take the phone waves, and you take the computer bits and combine them, and then send over and put a device here that can separate out the two. Basically these bits are coded at much higher frequencies. So this one is coded up to 4 kilohertz, and this one is coded from higher frequency like 20 kilohertz to maybe 1 megahertz. So there is a frequency division multiplexing here, and then here those frequencies are taken out, and then you can get the bits out. So basically this is what is called DSL. DSL stands for digital subscriber line, and this is your subscriber line. This is the line which goes from the phone company to the subscriber, which is your home. Once that becomes digital, that is called DSL, and now you are not limited to 56 kilobits. You can go up to as much as you want. I mean, I have a service at 18 megabits, which is the highest available in St. Louis. But as I said, in Japan and Korea and other places, you can get up to 100 megabits. Okay. And then the cable company can give you high speed too. Basically, what they do is they already have a cable which runs all through the streets and to your home, which is very high frequency, which is a very high, which can pass very high frequencies. So they can use some frequency band for data, some for voice, and some for TV. For phone, all you need is 4 kilohertz. For video, you need up to 500 megahertz. And you need 6 megahertz for TV per channel. So if you have one channel, you need 6 megahertz. If you are getting a 70 channel from the cable company, you have to multiply that by 70. So 70 times 6, so that many megahertz. But the video cable is good. It can take up to 500 megahertz. Alright, and therefore, given that we use one channel for data, suppose we use one channel for data and we do 5 bits per hertz. If we do 5 bits per hertz, out of 6 megahertz we can get 30 megabits. Okay, and so normally the phone company, the cable companies offer service like this where 30 megabits down and 1 megabit up. The up speed is always lower for many reasons that we learn about when we learn about physical layer. So the down speed is 30, the up speed is 1. However, this cable does not go from your home to the cable company. What they do is they take it to some neighborhood and then they switch on to fiber, and the fiber goes to the cable company. So that is why it is called hybrid fiber coax, HFC. It's a combination of fiber and the coax cable. In some places, they have moved forward and they bring fiber to the home, and that is called FTTH. In the case of fiber to the home, what happens is that the whole thing comes on a fiber, and then at some places they have what we call splitters. So the light that is coming from here goes to all the fibers that are split and goes to all the homes. So this is called optical line terminal, and this is called optical network unit, ONU and OLT. So everything that you want to send, that you want to receive, such as Ethernet or T1E1 or frame relay or telephone or video, all of that can be sent on the fiber. And since this is passive, this goes to every home, same thing goes to every home, and your ONU can select whatever is for your home and give it to you. Alright, and since this is passive means there is no electrical power required. This is a simple splitter. There is no electrical power required. This is very reliable. They can put it on the curves. If they needed a power there, then it can go bad and they have to send trucks to repair it and all that. So that's why this is also called passive optical network, PON, because of its reliability. So like I said, I don't think we have in St. Louis FTTH fiber to the home, but in some cities we do. And again, in other countries it's much more common. And again, the two countries that I keep telling you so many times is Japan and Korea. Okay, I was involved in a PON company, and I know our customers were all in Japan and Korea. We just made trips to Japan and Korea. All right. The next way to get to the network is wireless. And by wireless, we have Wi-Fi hotspot, cellular access, telephone, or WiMAX. So WiMAX actually is a new network that is just coming up and actually available in St. Louis. And when you buy a computer nowadays, it might even have a WiMAX. My computer, for example, the one that is in front of me here, has a WiMAX chip in it. And Clearwire is offering the service here. If I were to get that service, it's like cellular service. I can go anywhere on the road, on the car, in the park, forest park, and I would be able to get very high speed access. Sometimes they call it 4G, which is a misnomer because WiMAX is 3G, but they call it 4G because it is much faster than 3G, the current 3G. So I mean, this is a name issue, but anyway. But the good thing about WiMAX is it goes as far as a cellular signal goes, but it goes at the speed at which Wi-Fi goes. The cellular signal is in terms of data rate, is very low rate data rate, right? But WiMAX gives you very high data rate like Wi-Fi. So it takes the best of Wi-Fi and the best of cellular. It takes the distance from the cellular, it takes the speed from Wi-Fi. So you can use it, you can basically, from one tower, you can light up almost a city, 4 or 5 kilometers. And you can even, use it while moving, just like a cellular phone. That's all about the access. So we talked about the access, many different methods. We started with the modem, then we went to DSL, then we went to cable, fiber, and then the wireless. Those are all methods for access. So now we are back to networks, and then we want to measure the performance. So this next few slides are slightly different. Before I go into those, any question about the access networks? None? Then we move on to this, basically 3 methods of measuring the performance. Delay. First thing we measure about a packet is how long will it take. And so the delay consists of several parts. First is how long will it take. Say here's an example. So we want to send 640,000 bits over a circuit switch networks, and all the links are 1.536 megabits per second. Each link is shared by 24 users and 500 milliseconds to establish end-to-end circuit. So since this is a circuit switch network, just like a phone network, before you can send your first bit, you have to set up the circuit. That takes 500 milliseconds. Once you have set up the circuit, then you can send them either at 1/24th of this rate, in which case you just using 1/24th, you are a single user. Or if you are a company, you could get the whole line for yourself, for the company, and you can send at that rate. So there was a question asked last time. Let me see who asked that question. You had asked as to whether that related to this. Basically, the way phone line works is that the phone company right now takes 24 phone lines and puts them on one circuit. That is called a T1 circuit. Okay? Each phone line is 64 kilobits. What happens is whatever you speak is digitized at 8 kilohertz, 8,000 samples per second. Each sample is 8-bit long. So if you do 8 bits 8,000 times in a second, you get 64,000 bits per second. Okay? Now you take 24 users, so you multiply 64 by 24, you get 1536. Okay? That is one circuit that the telephone company uses, that is called a T1 circuit. If you are a company, you could just ask for a T1 circuit, you get 24 lines, and then you can use them for anything you want, for data, for voice, or whatever. Alright? So if you look on the wire, what you will see is 24 slots. First slot for the first user, second slot for the second user, third slot for the third user, fourth slot for the fourth user. 24 slots in a particular time, and then cycle resumes again. Basically, then again 24 users. So all this happens, at a certain rate. And so your question was, what was your question again?
The question was, when you read a sentence like links are 1.536, how do you know that this is for the whole frame or just for your scores?
Yeah, so this depends upon what you have subscribed to. So it will be clear in our problems, but the book talks about how the telephone company works. So the whole frame is 1.536. Each user gets 64 kilobits. Right? Now some users can get 2 lines, some user can get 24 lines. Some user can get 1 line. Right? So it will be clear to you as to what it is meant. For example, in this example, we are talking about 1 user. So 1 user will get only 64 kilobit, and therefore to transmit 640 kilobit, it will take 10 seconds. If it was a WASU, and WASU probably has many T1 links. Right? We cannot live with just 24 phone lines. We need probably 200 telephone lines or something like that. So we have many T1 circuit, and so whatever rate you have, you just do that. Okay. And the second thing is that these rates somehow will come into your brain. Like for example, for us who work on these things, we remember 1.536 T1, T3 is 45 megabits. T4 is something. All those numbers we remember because we work on them so often, right? But it will be clear whenever the problem is given to you as to what you have for usage.
English, it was just an ambiguous sentence.
A sentence, okay, all right. Okay, all right, so now it will take 10 seconds to send that many bits, but it will take 0.5 seconds to set up the connection. So the total time for that file would be 10.5 seconds. So everybody understood as to how we got that 10.5 seconds? On a circuit switch networks, you need to set up a circuit and then send the bits. On a packet switch networks, you don't need to set up the circuit. You can start sending the bits, but you have to packetize it, so there is an overhead per packet. So let's talk about packet switching. On the packet switching, first you have to collect the bits as they're coming in, make a packet, add the header, put them in the queue. So there is a queuing delay as well. So there is a queuing delay because you are waiting. First there is a processing delay, then there is a queuing delay, then there is a transmission delay, and there is a propagation delay. So what is transmission, what is propagation? Transmission is for the bits to get on the wire. You see, when you have packet which is so big, first bit gets on the wire, then the second bit gets on the wire, and the third bit gets on the wire. So let's say your packet is 512 bits, all 512 bits got on the wire, and then they move slowly to the destination. Right, so that is the propagation delay. Propagation delay is the delay to go on the wire and to move on the wire, right? And the transmission delay is the delay to get on the wire. You understand the difference? First, the bits have to leave the computer and get on the wire. That is transmission. Once they are on the wire, depending upon the length of the wire, they have to propagate. If the wire is 2,000 kilometers, there will be a lot of propagation delay, but the transmission delay will still be the same. Transmission delay simply depends upon how many bits per second you are transmitting and how many bits you have. Right? The propagation delay depends upon the distance. So that depends upon the distance and the speed of the signal. And the speed of the signal is speed of the light, which is 3 times 10 raised to 8 meters per second. That is also the speed of electricity. Well, actually, the speed of signal changes on different things. So the speed of the light in vacuum is 3 times 10 raised to 8 meters per second. But if you are sending it on the fiber, it is only 2 times 10 raised to 8 meters per second. Yeah.
If the propagation delay is longer than the transmission delay, do you run into problems then?
There is no problem. So you could have lines which are very long, you could have lines which are very short. You just have to know that there are two distances. One is the distance get on the wire, and second is second is for the bits to reach the destination. There is no problem. Okay. So all right. So we have to consider 4 delays. Processing delay, which is basically inside the computer, where you have to check out everything, make the packets, and check the CRC. Check that there is no error, nothing like that. Then you have to put them behind other packets. There might be a queuing delay, then there is a transmission delay, and then there is a propagation delay. Okay, so as shown here, first there is something that you need inside the computer, then you have to stand in the queue. Once you get your turn, then you have to get onto the wire, and then once you get on the wire, you propagate. So here is an example. You want to send 1500 bytes on 10 megabit per second Ethernet, and the length is 1 kilometer. So first of all, transmission depends upon the packet size, because you want to get onto the wire. What is the speed? What speed we can get on? 10 megabits. And how long is the packet? 1500 byte. So how long will it take for the 1500 byte to get out of the computer at 10 megabit? It will take 1500 times 8. Why 8? Bits per byte. And divided by 10 mega. 10 times 10 raised to 6. That gives you 1200 microsecond or 1.2 millisecond. This is just the time that a packet takes to get out of the computer, get on the wire. Then the bits will travel to the other end, which is 1 kilometer away. And how long will it take for 1 kilometer? Since they are going on the fiber, we use the speed of 2 times 10 raised to 8. And this is 1000 meters, it takes 5 microseconds. Alright, so it will take 1.2 millisecond for the transmission delay and 5 microsecond for the propagation delay. So that is the total delay. Actually, one delay which we have not calculated here is the queuing delay. It turns out, as you can see here in this example, the propagation delay is generally small. What is large is the queuing delay, which is not shown here. Queuing delay could be very large. You could be waiting inside the queue, particularly in a router where lots of people are sending the packets, and then they stand in the queue to get out of the router. Alright, so that finishes delay part. So the key lesson is that if it is circuit switched, you have two delays. What are those two delays? Circuit setup and then the transmission, right? Basically the propagation or whatever you want to call it, propagation delay. Yeah. If it is packet switched, then there are 4 delays. First is the preparation time, second is the queuing delay, third is the transmission, and fourth is the propagation. Okay? Propagation depends upon the distance and the speed of the light. It does not depend upon whether you are going at 10 megabits or 100 megabits. You are still going 2 times 10 raised to 8. By the way, that number 2 times 10 raised to 8, we all remember how. That number, speed of light, there are 2 ways to remember it. One is that we remember that it is 3 times 10 raised to 8. That's kind of difficult to remember, but if you just remember 300 meters per microsecond, 300 meters per microsecond, that's much easier to remember. Because then the power goes away. 300 meters per microsecond. Second way we remember is actually, this is fiber thing which we use more often, is just this number. In our daily calculations, we know that it takes 5 microseconds per kilometer, period, that's it. 5 microseconds per kilometer. So if somebody says that I have a link which is 20 kilometers, we just multiply by 5 microseconds, and we know it is 100 microseconds. So those are the 2 numbers you can remember. Either 5 microseconds per kilometer for the fiber, speed of light in fiber, or if you want to know the speed of light, then 300 meters per microsecond. Either one. Alright, so now we move on to the next measure of performance, and that is throughput. Throughput is measured in bits per second. And somebody says capacity. Capacity means nominal throughput, and when we don't say capacity, we mean throughput, we means realistic. So what's the difference? The difference is nominal is what we use in the sales literature. That is the maximum possible. Actually, it is not even possible, but that is the rate at which we generally sell. For example, when you buy a Wi-Fi device, they say, let's say it is 802.11g device. They say it runs at 56 megabits. If you put it on your computer and measure, you will never get any more than 20 megabits. 56 megabit it is sold at, but you will never get any more than 20 megabits. So that 50 megabits per second is actually what is called nominal capacity. That is what each bit, if you were to take one bit in the air and measure it, it will be 56 megabit going per second. But you are not going to use every bit time there, because a lot of bit time on the wireless, you have to wait, you have to collide, and you have to retransmit, and so on and so forth. So what you really get in real, and there is a lot of bits which are lost in the headers. So what you really get as useful throughput is 20. So your throughput is 20 megabits, but the capacity is 56. So that is the nominal capacity, nominal throughput. Now, if you have many links along the path, your throughput will be determined by the bottleneck. So let's say you have 100 megabits to the first router, then there is a gigabit between 2 routers, and then 10 megabit to the next computer. What is the speed you will get on this path? 10 megabit. Right? So the end-to-end capacity is only 10 megabit. Actual throughput will be less due to sharing and overhead. But if suppose you have this connection, if you measure, you will not get 10 megabits even, because again some bits will be lost in the retransmissions and overhead and the packets and headers and so on and so forth. So that's the thing, yeah.
So but it's still better, even though the worst, weakest link is 10 megabits. It's still better than if all 3 of those wires were 10 megabits, right? Because part of the journey is still faster.
Well, no. Okay, let me just say one more time. The propagation delay does not depend upon the speed. All right, propagation delay depends upon the distance, right? This 100 megabit does get the packets on the wire faster from here. This gigabit does get the packets from this router on the wire faster here. However, if you don't do things right, it is quite possible that a lot of packets can come in here at gigabits and they are not able to get out, so the queues are very big and the packets start getting lost. Okay, this was the problem 30 years ago when I did my PhD thesis, and that was one of the things that we worked on, congestion control. What should we do if this happens? And so nowadays it doesn't matter, because nowadays we have congestion control in the protocols. So if that happens, now we have protocols that will stop the source from sending any more rather than dropping the packets. But originally all we did was just drop the packet, and that was bad. Okay, so your observation is correct that if you given that you want you see, another reason you might need a gigabit line here is because not everybody is going here. Some of them might be going there, some other way, and so this line is in the center, and therefore it has to be high speed, and it is shared by a lot more people. But so that is correct that it is better to have as high speed as you can get, although you have to be careful that if you have very unbalanced network, then you can get into trouble.
So what is it telling you that when you said net end-to-end capacity is 10 megabits?
Yeah, that means between this computer and this computer, between these two computers, you cannot send any more than 10. Between these two computers, but you can send another 10 to that other computer, another 10 to that computer, some other computer. Other. So, for example, when you have a DSL at home, you might have some speed. Let's say I have 18 megabits, so then 18 megabit is the maximum I can get from Google. Google has gigabit capacity, but I can't get that because I have 18 megabits. Period. Okay, so that's the end-to-end, depends on the bottleneck. Now, so the third measure is the loss. If the packets get queued and they don't get out, then you have a loss. And so that and also if the packets have bit errors, then there is a loss. If one bit in the packet goes wrong, then there are two possibilities. That you have an error correcting code and you can correct that bit, which most of us don't, by the way. And the networks, we don't use error correction. So only thing is the packet has to be thrown away. If we find a packet, every packet is checked, and if there is any single bit error, we just throw it away. Yeah.
What causes a bit error?
What causes a bit error is that if you remember this coding thing, if I send this pulses and something like this, right, it is quite possible that depending upon the distance, this will become smaller and smaller and smaller pulse. At some point, the pulse will become so small that the receiver cannot recognize it. Okay, and that will cause a bit error. When you send it on the air, wireless, if somebody else sends it at the same time, that will cause a bit error. Right? Any interference will cause a bit error. Yeah.
How can you tell?
How could you tell? So we will talk about that when we go to the CRC, cyclic redundancy checks. So we put check bits at the end in every packet. If these check bits don't match, then we know that the bits are in error. It's like your credit card number. Credit card number, if you gave somebody credit card number, they don't have to go to the bank to figure out that this number, one digit was wrong, because there is a check digit at the end, extra digit.
Does the bias signal get weaker while they're waiting?
Okay, so the question is, does the signal get weaker while they're waiting? No. See, what happens when you're waiting, you're in the memory. In the memory, it is continuously being refreshed. But on the wire, there is no electricity. I mean, basically on the wire, it just as it goes farther, it becomes smaller and smaller and smaller. But in the memory, it doesn't. All right, so that brings us to this homework 1B. Let's read the homework. Consider two hosts A and B connected by a single link of rate R BPS. So the rate is given in a symbol R. Suppose that the two hosts are separated by m meters. So the distance is given, and suppose that the propagation speed is s meters per second. Host A is to send a packet of L bits. So we are giving you all the numbers but in symbol form, right? So find out what is the propagation delay. So you can find the propagation delay given the distance and the speed of light, whatnot. Find the transmission time. Ignore the processing queuing delays and obtain the expression for end-to-end delay. Right? And then suppose the host A begins to transmit the packet at time t equal to 0, and where is the last bit of the packet? So the question is, you begin transmitting, where is the last bit of the packet? It depends upon the length of the link. If the link is very short and the packet is very big, the last bit might still be in the host, in the source. On the other hand, if the link is very long, then the last bit must be on the wire, somewhere close to the destination. Right? So that's what it is asking. Where is the last bit? Suppose D prop is greater than D trans. Now this is similar to the question that was asked. Propagation delay and the transmission delay. If the transmission delay is small, means the very high speed link, but the propagation delay is long, there is something which happens. So if D prop is greater than D trans, where is the first bit of the packet? If it is less, where is the first bit of the packet, and so on and so forth. And then we give you the numbers G. Suppose the packet size and the speed and all those numbers are given, then find this one. By the way, this is problem number 5 from the book, P5. So this is the problem in the book. I have written it down on the slide just for you, but basically all you have to do is use something similar to what we did here. We did by an example, and there we are asking you to write the formula. Sorry. Where am I? Yeah. Sorry, there was first question here. Was there a question on this side? Yeah, I will come to.
On DE and so on, do you want us to just say if it's on the wire or inside the switch, or do you want the distance?
Yeah, where is the first bit of the packet? So basically, so there are three possibilities. The first bit of the packet would be on the wire, okay, or it could be in the destination. That's all. So basically 3 positions: at this source, on the wire, or the destination. Right? Source, destination, or the wire. A question?
So for C, you say ignoring processing queuing delays. Can you ignore processing delays and queuing delays?
And the queuing delay, yeah, right. We haven't talked about processing delay and queuing delay anywhere in this lecture yet today, because those are difficult to compute. We're just talking transmission and propagation. All right. Now we go into protocol layers, and this is actually one of the most fundamental lectures in networking. Protocol layers. So listen carefully. Here is the problem. There are two philosophers who want to discuss this problem. Is there a God? Right? Now the problem is that they don't speak the same language though. So there is a problem that they speak the different languages, and that they are communicating through a telex system. And now most of you don't know what telex system is, but there used to be a system where you used to just click things, bit, and then they will be received by a telex machine at the other end. So we need 3 people. We need many people actually. So this philosopher says something, and since he speaks only French and not English, maybe he speaks English and this guy speaks French, that has to be translated into the other language. So we need a translator here, or some common language. Then it has to be telexed. It has to be sent to the other side, and then it has to be received here, then given it to a translator which translates it into French. So we need 2 things to be done to the message. One is it has to be translated. Second thing, it has to be transmitted. Right? So what we do is we make 3 layers, we make 3 protocols. One protocol whose job is simply to translate. And we write another program whose job is simply to transmit and receive. Right? So this problem of discussion between any 2 people who don't speak the same language and are far away requires 3 layers. Right? First layer is what we call the application layer. These people, they know philosophy, but they don't know about translation business and they don't know about the transmission business. Then the second layer, they don't know philosophy. They are not the philosophers, but they know translation. And then the third layer, this person, they don't know anything about philosophy or the translation. They just know that if A comes, I send A the other side. How to send the bits and how to receive the bits. So this is a division of work. It is much simpler to do all this if we divide the work into functions that can be handled by one layer. Based upon this, back in 1980s, the networking scientists sat down and said we need 7 layers. And the first layer is job is called application, will simply do the application that you want to do, which is file transfer, email, remote login. These are all applications. Second layer is presentation, and this somehow understand that whether it is an ASCII file or a sound file or a video file or whatever it is, so it knows when the message comes in whether to present it on a TV or write a text on the screen, what to do with this, right? So the presentation layer simply presents the message. Session layer establishes the connection. Transport layer manages the end-to-end communication, and it will become more clear when we go to TCP. The network layer simply does the routing, and the data link layer only uses one hop. So data link layer only sends from one computer to the next computer, which is directly connected. The routing layer do actually more than one computer. So if you want to go from here to there, first the data link layer will send it here, and then routing will decide that it has to go that way, and then data link layer will send there, then the routing has to decide that it has to go that way. So there is routing layer and the data link layer. Data link layer is 2-party, but routing is for the whole network. And then the physical layer. Physical layer does nothing except sending bits. It knows that for a 0 I have to send a transition down, for a 1 I have to send a transition up. So that's the only thing it does. When it gets a set of bits, the physical layer decides how to send those bits. Alright? This is called ISO. What is ISO? International Standards Organization. International Standards Organization. It's like international. What is it? We have in New York. We have the Worldwide Organization. Huh? Loudly, say loudly so I can hear it. Well, no, actually, so basically I was thinking more of the national, UN, United Nations. All right. So just like ISO is United Nations part, actually it's part of United Nations, but that is for standards. Every country comes to ISO and says this is what we want to make a standard, and then if it becomes agreed, then it becomes the ISO standard. So it's like UN making saying that okay, we all should go to Libya or something like that. Similarly, in ISO we decide as to how the bits should go. All right. So ISO is the organization, International Standards Organization, and they have many things, but this is the reference model. It's called OSI, Open System Interconnection. Open System Interconnection because previous to this there were many systems which were closed, such as we worked for digital, I worked for digital equipment, we had our system, IBM had their system, Xerox had their system, Apple had their system, everybody had their own systems. So when OSI came about, this was supposed to be open, that means everybody will use it. Alright? And that has 7 layers. Right? Each layer had its job. It turns out that just too many layers. We don't need 7. And so in practice, we need only 3, 4, or 5. And so these 2 layers are generally combined. Data link and physical are combined. The network and transport are generally very much related. And then session, presentation, and applications are combined. But before we get into that detail, there are 2 more terms about the ISO OSI model that we might need later on in this course. And I want to emphasize them because they're not very well described in the book. First is the session and protocol data units. So when a transport layer talks to the transport layer, they use a message between them which is called protocol data unit, PDU. And so there is a transport PDU, there is a network PDU, there is a data link PDU, and there is an application PDU. So when one layer talks to the other layer, that is called a PDU, right? When same level at the other side. When the higher layer talks to the lower layer, that is called the SDU. So whatever the transport gets from the application layer is called transport service data unit. Whatever network gets from the transport is called network service data unit, NSDU, TSDU, and so on and so forth. This would be TPDU, NPDU, and so on and so forth. And these are all service access points. So when you talk to the lower layer, you talk to a service access point. So there is a transport service access point. All right. So now we introduce 3 terms: access points, service data units, and protocol data units. Service data units flow downwards or upwards. So this is SDU coming down, and PDUs flow horizontal, and so on and so forth. Right. So here is the full detail. Anything that is coming from the application to the presentation is called PSDU, Presentation Service Data Unit. Something that flows from presentation to the session is called SSDU, Session Service Data Unit. This is Transport Service Data Unit, Network Service Data Unit, Data Link Service Data Unit, File Layer Service Data Unit. Things which go in horizontal direction between the applications, that is called APDU, PPDU is Presentation Protocol Data Unit, Session Protocol Data Unit, Transport Protocol Data Unit, and so on and so forth. And when the request comes in, then they have another term. So the higher layer will make a request to the lower layer, that will go to the other side, and then the other side will make a request to the higher layer. So this is called the request, and this is called the indication. 1 is the request and 2 is the indication. 3 is the response and 4 is called the confirm. Okay, so you could have unconfirmed service. If you have unconfirmed service, then this doesn't happen. You just make a request and indication. Alright, TCP/IP, which is the protocol that we use today, was done before ISO OSI. ISO OSI was done in 1984. TCP/IP was done in 1974, 10 years earlier. And in 1974, as I said, before 1984, there were lots of protocols. Digital had its own, and I said IBM had its own, and the universities had their own, which was TCP/IP. And so we in the industry really didn't care for TCP/IP that much because this was a non-standard researchy thing. And we were working on OSI model, ISO OSI. But suddenly something happened, and now the whole OSI thing is gone away, and only thing left is TCP/IP. All right. So TCP/IP did not follow the OSI model because it was before that, before OSI model. However, after the OSI model was developed, TCP people said, no, we have layers too. We have layers too, and here is our layer model. So here is their layer model. which we'll talk about, but it's not very clean because they did not know about the layers when they designed it. Your question?
I was going to ask what happened.
No. Basically is that TCP/IP was made public by NSF, and so there is a whole history there as to why it became famous. But anyway, so this is what it is. The TCP/IP, when they designed TCP/IP, they did have applications which ran either on TCP or UDP, and TCP and UDP run on IP, and IP runs on Ethernet or point-to-point or packet radio, which run on coax or fiber or wireless. So this could be called the physical layer. This used to be called host to network layer, which can be similar to the data link layer. This is called internet protocol, that can be called the network layer. This is the transport layer, and then the application layer. So there is maximum of 5 layers. There is no session, there is no presentation. All right, and not only that, these are not really layers. TCP/IP are very much like this. You cannot separate them. You cannot run TCP on any other network protocol. So they are not layer. Layer means that you could change the layer below and things will still work. All right. But having said that, this is it. Basically, this has survived. And so in the rest of this lecture, this class, we will teach you about TCP, we will teach about UDP, we will teach about IP, FTP, and so on and so forth. All of these things. And we'll call them layers, but they are not very clean layers. Okay? All right. Now, this particular book that we are using in this course follows a special model, which means top-down. It says somewhere top-down approach. So we start with the application layers, and then we move to transport layer, then we move to IP layer, then we move to the lower layers, and so on and so forth. There are other books that we have used in the past that go bottom up. That will do the physical layer first, then data link layer. There are third set of books that really don't follow any of this, and they hold different approach. So anyway, so every author, every book has its own approach. We will follow the top-down. So how the OSI and TCP match? Well, OSI says application layer, which is actually not complete application. It is application plus half of the session. When they say TCP, the transport layer, it has half of the session and the OSI transport layer. When they say IP, it is not complete network layer. It has part of the network layer, and then part of it goes into what we call the access here and the data link. So there is no one-to-one match with OSI. And it doesn't really matter now because there is no OSI. But sometimes we use the OSI terms. For example, we say layer 3. It's very common for people to say layer 3. So what is layer 3? Well, by layer 3 we means IP. Sometimes we say layer 4, we mean TCP. Even though this is somewhere between 4 and 5, we say layer 4, we mean TCP. We say layer 7. Now, there is no 7th layer here, but in TCP IP, if we are sitting in a meeting and we say layer 7, we mean application, period. Okay, which is this layer 7. This is layer 7. Could be called layer 5 as well, but we don't call it layer 5, we call it layer 7. So you know how layer 7 came about. You can't clearly say, well, there are not 7 layers, but this is layer 7 because OSI had it at 7th layer. This is layer 3 because OSI had it at layer 3. All right. In fact, we use the term L2, L3, L7. L2 is layer 2, L3 is layer 3. So OSI introduced the concept of services, interface, and protocols. They were force-fitted to TCP later. It's not easy to replace protocols in TCP. So TCP, as I said, TCP and IP are very much merged. When we make a TCP packet, we put the IP header in it first. So you cannot run TCP on any other protocol. In OSI reference model was done before the protocols, and in the TCP world, protocols were done before the models. In TCP world, when it was designed, the design principle was implemented. If it works, then we make it a standard. In the standards world, they make it a standard first and then you implement it. Okay, so that's a different philosophy. OSI, standardize first, build later. In TCP, build first, standardize later. So OSI took too long to standardize. They took 5 to 10 years to write a standard. By the time people said forget it. Okay, so then it never happened. TCP was already in use by that time. OSI became too complex. TCP is not general, but it works. So how these layers work? The way these layers work is that you take the user data. Let's say you want to send a message, I believe in God, right? That's the user data. You put a TCP header on it, so you put some more bytes in front of it. Then you give it to the IP. IP puts some IP header in front of it. Then you give it to the Ethernet or any other subnetwork that you're using, and that puts header in front of it. So when you see, if you see the packet on the wire, it has the subnetwork header, then it has the IP header, then it has the TCP header, and behind that is the user data. When it goes to the other side, the subnetwork layer reads the header and does whatever the header says and gives it to the IP, removes its header and gives it to the IP. Right? And the other side, IP reads the IP header and does whatever it's supposed to do by that header and then gives it to TCP. So TCP only gets this much. Then the TCP reads the TCP header and removes itself and then gives to the user data. So user application only gets the user data and does not know what happened to the packet on the other layers. Right? And what was in the header in the other layers, it doesn't know that. Alright, so what are the applications? TCP has many applications such as BGP, FTP, STTP, SMTP, Telnet, SNMP. Some of these applications run on TCP, some run on UDP. So there are two transports, and we will talk about both of them when the time comes. So we'll start from here. We'll top down we are going. So we'll talk about these applications first, then we'll talk about TCP and UDP. Then we'll come to IP and down. Now, in addition to IP, there are some protocols here in TCP IP protocol stack called ICMP, IGMP, OSPF, RSVP, etc., etc. They don't really fit very well, but they are required for operations, so we'll talk about them as they come. Anyway, so the idea is that there is a layers and that there are headers are added each layer, and then the packets go to the other side, and then the headers are taken off. So we are going to finish this chapter. So the thing is about security. We are going to talk about different aspects of security, so let's get on to that. First is, when we say security, we mean three things. CIA. If you want to remember what do we do in security, we remember CIA. CIA stands for confidentiality, integrity, and availability. We want to make sure that nobody can read. Confidentiality means that nobody can read our data. Integrity means that nobody can change the data. Suppose somebody can read it. That's not a problem, but I don't want anybody to change it. Right? It's like your homework. When you submit it, you probably, confidentiality is not there, but you want to make sure that nobody changes the homework before it gets graded, right? Then you need integrity. Availability means that people who are supposed to get it and other people don't. So for example, if somebody does a DOS attack, we call it denial of service attack, where you send so many requests to a computer, to a server, that really the people who are supposed to get it, use the server, cannot use it, and server is totally overloaded. So that is called denial of applicability. That is called unavailability. So you combine all these things and you get CIA. And actually, the course that I'm teaching in the same room before this course is called network security. So we go into whole semester detail of what I'm going to do in a few slides here. But so next thing to know about is what are the bad things that can happen to your computer. So first is the virus. What is a virus? Virus is a code that attaches itself to programs, disk, or memory to propagate itself. So the virus is something that is a method of how it propagates. It can attach to a disk, and when you put the disk on the next computer, it can appear there. It can attach to a program. When you run the program on the next computer, it can appear there, or it can be on the memory. On the other hand, worms are different. Worms install itself on another machine by finding username and password. So they travel by network, right? So if you have 5 computers and you use the same username and password on those 5 computers, a worm will know that your username is this, password this. It will try it on the other computer, and if it succeeds, it will move. Okay. Trojan horse. Now everybody knows the story of Trojan horse. Basically, that's a Roman war. In the Roman war, what happened was that when the army could not get into the fort, they made a toy horse. A horse which was made of wood, and it looked like something for entertainment, and they brought it inside the fort, and then the whole army of people came out of that wooden horse. That is called a Trojan horse. A Trojan horse is something that comes out as an entertainment, but really, kills the people inside, right? So it's like you download something from the internet. It looks like something useful to you. It might say a movie name, or it might say something else, or some utility which is useful to you. But when you execute it, it infects your computer. That is a Trojan horse. Trojan horse pretends to be utility and convinces users to install it on their PC, but when you install it, it just, is bad. Spyware is something that collects data about you and sends it to somebody else. So it's not a virus. It's a spyware because they know what you are buying, what you are selling. So here is an interesting exercise you can do. Go to Google, do a search on some topic. Let's say you do a search on mortgage rates. Next day, count how many emails you get about mortgage offers. You'll be surprised. Everything that you are doing is being monitored. Somebody is monitoring that you are looking for a mortgage rate, so all the banks will start sending you this thing. Do a search on shipping or something, and then you get a message all about shipping. Do a search on pool, and then you get a message about pool. So that is spyware. There are programs on your computer which monitor every activity that you do, and then they tell somebody that, okay, this guy is searching for this, and then they make use of that. Hoax. They use so they will say, well, here the last bit. If you just send this message to all 100 people, you will get this and that, and the guy will be cured. And there may not be a guy at all. There may not be a child at all, but that is just to collect a lot of information. Trapdoor. Trapdoor is slightly different. It's something that the developers of the software put. So you might download an FTP program or something else, it doesn't matter. And they might have a way of getting into that program from anywhere. So for example, simple example is I have a DSL modem, and so I called the DSL company that I have a problem with this modem. They said, okay, let me log into your DSL modem. So they were able to log into my DSL modem and see everything without anything. So they have a trapdoor. Right? And if they wanted to, they could probably monitor every bit that I'm sending, on the net. Logic bomb. Logic bomb is an instruction that triggers on some event in the future. So it's a time bomb where they say, okay, on day 1st January 2000 or whatever, something was supposed to happen. Nothing really happened actually, but people could put a time logic bomb where on a particular date and time things will happen. A zombie is an instruction that can be triggered remotely. So this is something that can be done, is that once the virus is on your computer, one form of virus is a remote control. Basically the people somewhere else can send something to that program and will do whatever they say. They might say, please send a request to Amazon. If they send it to 100 computers, or if they send it to 10,000 computers, 10,000 requests will be sent to Amazon. Amazon will be busy resolving those requests, and nothing will. Basically, this is a kind of denial of service attack. This is also called a botnet. A botnet is where there are computers that can be controlled remotely by bad guys. Okay, so Jambi. So anyway, so what happens is this can also be used for other kinds of attacks. For example, a Jambi could be ordered to send an email. So your computer could send out, for example, once I got infected, my computer was asked to send out 1,000 emails to all my people on my list, and email of some kind, but I don't know what the email was, but I did get a message from the support saying that your computer is just going crazy, it is sending out so many emails. And then we had to find the problem and fix it. Right? So these are all different kinds of malware that we talk about in the security course, and we talk about how to get rid of them. We talk about types of attacks. So denial of service is one attack, which we talked about, flooding. Buffer overflow. So one way they can get into your computer is by causing a buffer overflow. And what happens with the buffer overflow is that if when you write a program, generally you put the things on the stack, and then you come back to the stack and return from a procedure call and all that, right? But if there's a buffer overflow, the computer doesn't know where to go. And in that case, they can program it so that it goes into their program, which is a bad virus or something like that, and gets executed. So that is the buffer overflow method. Malware, we already talked about. Brute force is that you can try all the passwords. For example, this week's homework for my network security people is to hack into our server and to find their password. So such things exist, right? Port scanning is that they want to find out what are the applications that are running on your computer, such as FTP server or web server, and then use them. Network mapping, trying to find out what computers are on your network. So all of these things can be done.